In this video, we're going to talk about conditional probabilities. Now, we've talked about these actually a few times so far, but now let's get the actual notation and the full calculation for it. Though, similar to other pieces, it's like there is a formula for it, but there's other ways to think about it that can get you to the same solution. So, conditional probabilities, the key is that there's some condition given. And what this condition does is it gives us a condition on the sample space. So with the rules that we've used so far, for the denominator of our fractions, we're typically using everything. So like we're going to go back to this data with the 72 chronic users of cocaine, and we had this kind of grand total for our sample space, that's 72. So for most calculations, 72 would stay our denominator. What happens with conditional probabilities is that it limits our sample space. It gives us some information about the group that we're looking at. Instead of looking at everyone, we're looking at a specific piece of the data. So with that, we might be limited to a single column or a single row. And when we do that, it changes our denominator. So what we're going to get in this section is changing denominator. So, before we get to the notation and the formula for it, let's just look at some examples. So some key words that are going to show up with conditional probabilities, you can see if, you can see the word given. There are other different ways that it can show up too, and you just want to see, like, other questions would have asked, like, what's the probability a participant did this? What's the probability a participant did that? And if it's just saying a participant, then you're looking out of everyone. But there's ways of phrasing it so that you're giving information about who that participant is before even looking for a probability. And it's that can bring through a condition. So before we get our notation, let's just think about the fractions that we would make here. And then I'll come back and fill in our notation and how we're calculating it. So if a person took the placebo, what's the probability that they had relapsed? So this wording after if here, if a person took the placebo, that right there is our condition, meaning we know that they're in the placebo group. So if a person took a placebo, then we know that they're one of those 24 people. So that's where our denominator changes, is that you go to the margin, and we know that we're looking at these 24 people in the placebo group. Then just restricted to that group, what's the probability of relapse? So it's like I'm stuck in that row right there, and I want to see how many people relapsed in that group. 20. So that would be a 20 out of 24 for this conditional probability, and then that would be a 0.8333. So we could say if a person took the placebo, there is an 83.33% chance they relapsed. So, some pieces to our fraction here. The numerator is coming from the intersection of both. They mention placebo in here, they mention relapse. That numerator is coming from the intersection of those two ideas. The denominator is coming from what was given, the information that we already knew. We knew they were in the placebo group, and that's what made our denominator. So let's see that again with some different information. So I'm going to clear out my table here. Given that a person had lithium, so if they were in the lithium group, so now we know they're in this group of 24 people. So we're going to have these 24 people being given lithium in the denominator. What's the probability that they did not relapse? So in that group, we want to see how many did not relapse, and that would be the 6 people. So for the numerator, 6 people that both did not relapse and were in the lithium group, and then the denominator was what was given, which was the condition that they were in the lithium group. So 6 out of 24, which is a 0.25. So given that a person had lithium, there is a 25% chance that they did not relapse. So this notation that we're going to see down here, and in fact, if we just focus on the fraction part on this right-hand side, it's exactly what we're seeing happen up above there. So in the numerator, how I was saying both characteristics are coming through, so that's where this numerator is the intersection of the two events, or it's that joint probability of both. Then in the denominator, it's coming from the probability of what was given, or the condition that they're giving to our sample space. So for notation, on the left-hand side here, this is notation that we use for conditional probabilities. How we read this is the probability of event A given event B. So that line there could just be replaced by the word given. In that on the right-hand side, we're talking about our condition, what's already been given to us. And then on the left-hand side is what we're looking for. So to fill in notation for up above here, for this first example, if I wanted to write this in the notation down below, if a person took placebo, so that's our condition. So if I have my line here, what I would say is this is looking for what's the probability that they relapsed given that they were taking the placebo. So it's just rearranging the wording a little bit, but that's exactly how that wording would work. And the key is noting what's the condition, and that would be on the right-hand side. For part B here, given that a person had lithium, what's the probability that they did not relapse? So what I could do is probability that they did not relapse given they're in the lithium group. I could have even used my complement notation if I wanted to, like if you wanted to use R with a C, that's fine too, either way. But order does matter here because whatever's on the left, sorry, I'm getting my directions all mixed up. Whatever's on the right-hand side here is what goes in the denominator. Those are always connected to each other. So just be aware that the order in the conditional setup is important because it can switch around, which I'll actually show in this next example. I'll talk about independence in a second, but if we go to part C here, it's asking for probability, and I see that word given, so I could immediately set up my probability notation like this, given that a person relapsed. So given that they relapsed, what's the probability that they took the placebo? This right here is very similar to part A up above here, but the order is switched. In part A here, how we did it was that we knew we were in the placebo group, and of them, what's the probability that they relapsed? What we're doing down below is switching it around, saying, we know that they relapsed. We know they're in this group of 48 people. What's the probability that they were taking the placebo? So with that, we're going to end up with this different calculation, and it's because we're looking at a different group of people. It isn't just placebo users. Now we switched it to everyone that had relapsed in this treatment. So for our probability down below, probability of both would be that 20 out of our given, which was relapse, the 48. Now, in terms of notation, just to kind of tie it to that formula that I showed up above, what we're technically doing is taking the probability of both over the probability of what was given. So that's where we're seeing that 20 in the numerator for that idea of how many were in both, out of our probability of the given, which was relapse, which is this 48. And technically, something that's going on here that we don't need to worry too much about, but just in case you're seeing this disconnect between that numerator is asking for a probability and we're just plugging in a whole number, but probability should always be between 0 and 1. Technically, this probability of having the placebo and relapsing would be 20 out of 72. And that denominator, probability of relapsing, would be 48 out of 72. That's technically what's happening. But with these conditional probabilities, you'll always be dividing the numerator and dividing the denominator by the same number, which if we deal with complex fractions, which we are just going to avoid, if we dealt with it, what ends up happening is they would just always cancel each other out. So we can skip a little step there and not worry about making the fraction in a numerator, fraction in a denominator, and just use the direct values coming from the table. And this would be a 0.4167. So that's conditional probability. You just want to be careful of the order and the wording that they're giving, and just be careful which is the condition and which is the probability that you're looking for. Now we talked about independence already, especially sampling with or without replacement, but something we might need to do is prove independence. And to prove independence, what we can do is try to show this calculation right here. So on the left-hand side, it's this probability of event A given that event B has already occurred. We want to see if that's the same thing as just probability of event A. If those two are the same, then they're independent of each other. What this would show is because, again, it's that this event B has already occurred, it's already true. So what we want to see is if that changes the probability of A. So let's take a scenario that we've talked about before, like flipping coins. We know flipping coins is independent. Say I wrote notation like this. What this would ask for is what's the probability of flipping heads given that I already flipped tails? Well, the coin's still 50-50. This would just be 50% chance. Probability of flipping heads given that I've seen tails before is just, there's still a 1 out of 2 chance that I flip heads. So this right there is the same thing as if I had just asked about what's the probability of flipping heads. I didn't need to say anything that I'd already seen tails because it's not changing anything. It doesn't matter what's already happened. The probability of flipping a coin and seeing heads is 50%. So this would prove independence. If they come out different, then they're not independent. If this changed in some way, kind of like we saw with drawing jelly beans without replacement, if those probabilities change trial to trial, then it's not independent. We'd have some dependence going on. So what we can do is use this rule to prove independence. So like, is the treatment and whether they relapsed independent? Now what we can do here is we basically want to show this rule up here, and we need a conditional probability to get us started. If you've already been doing calculations, it's kind of nice to just grab one that you've already done. But really, in this case, you can choose any outcome. So I'm going to choose just any treatment, desipramine, lithium, placebo. I can choose one, and one outcome, relapse or not relapse, and just look at the relationship between the two. Because if it's independent in one spot, it's going to be independent everywhere. And then if it's dependent in one spot, dependent everywhere. So I'm going to go ahead and use my result from part C. So what we found is the probability of taking the placebo given that they had relapsed was 0.4167. So what I want to do is compare this to the probability if I remove the condition. If I took out the idea that I already knew that they had previously relapsed, just what's the probability that they're in the placebo group? So this will show whether or not there's an effect of knowing that condition happened already. So probability of taking the placebo, there were 24 out of 72, which is 0.3333. So comparing those two numbers, those are not the same. What this actually shows is, so probability of being in the placebo group is a 33.33% chance. If we know that they relapsed, there's a higher chance that they were in the placebo group. So that shows there's a dependence between those two variables. Knowing one affects the probability, it can increase or decrease it based on that condition. So because those are not the same, they are not independent. When we do this independence test, if they're independent, they have to be exactly the same. So even if this came out to, I'll just write it down here, like if this came out to 0.4153, like something close by to 0.4167, still would not be independent. And I just made that number up. It didn't come from anywhere, but as close as it is, it has to come down to being the same fraction in order to be independent. So just be careful of that, that sometimes you might think that's close enough to be independent, but no, it would have to be exactly the same in order to prove independence.